Okay, so we were in the middle of part C on number 8, talking about when the first year that this country's budget is balanced. And what I was saying was that right here between year 10 and 11 is when column Y1 exceeds column Y2, and so we need to include this in our X domain for the window. So right now my window is from 0 to 15, which is actually big enough, so I'm just going to use that and then do zoom fit with that window, and then we'll do calc intersect and find when these two functions intersect. Okay, so now we can find the intersection, and it's at 10.47. So our answer is 10.47 years, but we actually want to know the calendar year. So there's a few things we should say about this this particular question. Because this is tax information and revenue information, revenues and expenditures, this is a discrete integer data set. So in other words, we only have one value per year for revenue and one value per year for expenditures. And what that means is that we would employ the slightly non-standard rounding scheme where we always round the value up to, so in this case we would round this up to 11, and that would mean that we were in 2017. Okay, so the other way to do this would be to just avoid the intersection altogether and just simply look at the table. And you can only do this because of this non-standard rounding scheme that I'm using here. And I know to do that because of the nature of the problem. But as you see here, the first year where we meet or exceed is in year 11. Okay. Okay, so that's number 8. Moving on, number 9. An investor deposits $1,600 into an account paying an annual rate of 3.35% compounded quarterly. And then we're going to find the model for this and then answer some questions. So this is a compounded growth model that we have. So we're going to use our formula for compound growth, which is this guy right here. Okay, and I know I'm going to need this to do this in the calculator, so I'm just going to put this directly into the calculator. But I want to be very careful that I don't lose parentheses anywhere, because we're going to need a lot of them. So my model is going to be 1,600 1 plus, and then I'm going to put another pair of parentheses here. So my APR is 3.35%, so that's 0.0335 divided by 4 because it's quarterly. That's 2 parentheses, and then I'm going to exponentiate this, and yet I'm going to do another pair of parentheses, and this is going to be to the 4x. Okay, so there's my model. And the first question after part A says find the amount in the account after 7 years. That's a vars y vars question. So I will evaluate my model after 7 years. And we have $2,020.87. 2020.87. That's rounding to 2 decimal places. Okay. Find the account's effective annual yield. This is part C. The EAY. So the EAY, we have a formula for that. And the EAY is 1 plus APR over n to the n minus 1. That's an equal sign there. And then if you want this to be in percent form, you need to multiply the whole thing times 100 once you're done, which typically we do. Okay, so let's go to the calculator and perform that computation. So the APR, or I'm sorry, the 1 plus APR over n, that's all this stuff here in the middle minus, without the x, okay? So I'm going to type that all out here. So that's 1 plus parentheses 0.0335 divided by 4, 2 parentheses, exponentiate to the 4th power, and then I'm going to get that value and then subtract 1 from it, and then finally I'll multiply it by 100 to put it in percent form. And that's our EAY, 3.39%. Or, I'm sorry, to 3 decimal places, so that'd be 3.392%. Okay. Part D. When the investor made the initial deposit, another bank was offering an annual rate of 3.33% compounded daily. Would the investor have been better opening an account with this bank instead? So basically what this question is asking us to do is to compute the EAY of this other account and see if it's bigger than 3.392%. And it's compounded daily, so that's going to be, our n value is 365. So let's do that computation. So that would be 1 plus 3.33 is 0.0333 divided by 365, and then exponentiate to the 365th power. Subtract 1, multiply by 100, and we get 3.385. So if we round that to the 3rd decimal place, that would be 3.386. And it is not better. So no, the investor would not have been better opening an account with this bank. This one's still better. Okay. Let's look at question 10. Moving away from financial stuff for a moment, find the half-life of a material that decays exponentially at a rate of 1.68% each month. Excuse me. So to find half-life, and when we are given the rate, so what we're going to do is assume that our initial value is 1, and then we're going to see how long it takes us to get to 1/2. So this is basically going to be a calc intersect question once we put our model in. And our model is going to be 1, and then if we're decaying at a rate of 1.68, that's 1 minus 0.0168 to the t. That's going to be our model. So we have to enter all this stuff in. And then, as I said, our y2 will be 1/2. And let's go to the table to see how long it's going to take this to happen. Oops, sorry about that. So it probably would be better to have jumped in increments of 5. Here it would have been faster. So it's going to take me a little while, but I can see it's going to be probably by 50 we'll get to it, I think. Yeah, so there it is at 40. We're getting there. So that gives me an idea for my window. So let's go to 50. And then we'll do zoom fit. and wait for that to think about it, and hopefully our graph will be usable. Okay, so we just got it down there in the corner. And our intersection is 40.91 months. This is in months. Okay. By the way, half-life questions can be sort of grouped into questions where you are looking for the half-life versus questions where you're given the half-life. A question where you're looking for the half-life generally is going to be a calc-intersect question. So ultimately you'll have to do calc-intersect to find that half-life. On the other hand, if you are given the half-life, generally what you'll do is you'll have to get the model using exponential regression. At least that's how I would do it. And so if you're given the half-life, you can typically use that to get the model via exponential regression and then answer whatever other questions are asked. All right, so let's take a look at number 11. The following data gives the average annual consumer price index from 2011 to 2016. We're asked to find the best fitting linear model. That's going to be linear regression for this data. And one thing to pay attention to is it does say the number of years after. So that's elapsed time. So we do need to reset the clock here before we perform any of these computations. I'm going to enter this data off camera here. So let me pause the video for a moment, and when we come back, I'll have the data entered. Okay, so I've entered the data in the calculator, and as I said, I did reset column L1 to start at time 0. That corresponds to year 2011. So make sure you do that, and the way I know that to do that is because it says number of years after. So that's an important point. If you don't do that, then you will be wrong on your answers here, at least on some of them. Okay, so now I'm going to do linear regression. I know to do linear because it says linear, so this is not exponential, so be careful. So number 4, L1, L2, vars, y vars, function y1, and there is our best fitting linear model, 2.897x plus 226.29. Okay. So question B says find the model's SSE. We can use the resid method here. So we'll go to sum, which is number 5. Number 7 is resid, and we want to square those residuals. And there is our SSE. 7.268. Our average error, we just need to take that SSE, divide it by 1, 2, 3, 4, 5, 6 data points. So divide it by 6, and then we need to take the square root of this number. And that's our average error, 1.101. Okay. To find the model's correlation coefficient, there's a couple of ways to do this. If you don't have diagnostics turned on in your calculator, then you can just go to vars, statistics, equation, and then number 7 is the correlation coefficient, and that's 0.9761. Okay. And then for part E, can we be 95% confident? Well, if we go to our critical value is 0.811, and then let's return to the slide. So yes, we can be, because 0.976 is larger than 0.8, whatever it was. All right, I've got to pause the video and then we'll stop here for the next part.